Today we are going to be starting some information about radicals. And it's going to feel a little bit like we're kind of taking a complete left turn, and it has nothing to do with what we were doing before, right? Factoring was so closely linked to polynomials, this sort of went right together. It's not exactly the case. We just need to fill in a little bit of information before we can sort of put all this information together. So, radicals is probably a word that you don't feel like you've heard before, you're familiar with. But a radical is an all-encompassing term, and one of the terms that it includes is a square root. And that, my students always say, oh yeah, I know what that is, okay? So when we are talking about inverse operations, we know that addition will undo subtraction, we know that multiplication will undo division, and we know that radicals will undo exponents. So there's really a lot of roots that exist. Okay, so we have an x squared that will be undone with a square root. And this is really the world we're going to focus in. But understand that like an exponent of 3 would be undone with a cube root. So there really truly in a square root is a little tiny 2 inside that little hook. Okay, but because it's the most common one, we don't write it. Okay, so an exponent of 10, we would undo with a 10th root. Okay, so yes, we are going to be focusing sort of here in this world of square roots, but all of those roots together are radicals. Now, we've already talked about factoring perfect squares, so those perfect squares, square roots, hopefully we feel okay with. So if we have something like the square root of 25, we know that the square root of 25 is 5 because 5 times 5 is 25, right? 5 squared is 25. We know that the square root of 36 is 6 because 6 times 6 is 36. Now, we've sort of left out this whole piece with square roots up until this point of time. But what would we do if we were given something like the square root of negative 36? Okay, and this opens a large can of worms, and we are not going to do all of it, but we are going to introduce the concept. The key here to understand is that there is not a negative number times a negative number that will ever equal a negative number. Right now, negative 6 times positive 6 is negative 36, but that's not a number times itself. So up until this point in your life, you have been living in the real number set, right? We know positives, we know negatives, we know fractions, we know decimals, we know repeating decimals. Okay, we're okay dealing with pi. Negative 36 falls outside of that world of numbers. The square root of negative 36 involves what we call I. So just like pi was this really weird decimal that went on for forever and never ended, right? We called that an irrational number. I is an imaginary number. Okay, and I is actually equal to the square root of negative 1. Okay, now I am not expecting you to actually deal with I or understand every single piece of I. What I need you to understand is that when we have the square root of a number that is negative, it doesn't fall within the real numbers that we've always been working with. So there is an answer for the square root of negative 36. It just falls within the imaginary number set. So at this point in time, we are going to say that this is a no real solution. Okay? It's not that there isn't a solution. The solution falls outside of the real number set. Okay, and the solution falls inside the imaginary number set. Okay, so we're gonna know that whenever, at any point in time, today, tomorrow, 2 weeks from now, if we get a negative underneath the square root, our answer is going to be no real solution. not because there isn't an answer, but because the answer falls inside the imaginary number set. So if you write no solution, I'm not going to give you full points because there is one. It's just not in the real number set. Okay. So at this point, we should know our perfect squares, like the square root of 25 is 5. If it's a large number, right, we could do it in our calculator. We would hit second, x squared, type in whatever number it is, equals, and we get the answer. If there's a negative, we know that it's a no real solution. But what about everything in between? Okay, so what if we have something like the square root of 8? Square roots, well, radicals altogether, are sort of like fractions. Okay, we know at this point in time that if we get a fraction of 3/6, we're not just going to leave it as 3/6, we're going to simplify it into 1/2, right? Because then everybody's talking about the same number and we have smaller numbers to work with. Square roots are the same way. They can often, not all the time, but often be simplified. And the way that we tell if a square root can be simplified is by deciding if there's a perfect square within it. Okay, so the square root of 8 can really be split up into 2 times 4. Okay, and 4 is a perfect square. So if I take the square root of 4 and I take the square root of 2 and I split those two pieces up, the square root of 4 we know is 2. And so the square root of 8 is the exact same thing as 2 square root 2. If you don't believe me, right, you can put it in your calculator. Oops, I didn't get the 8 in there. Right, we get this big old long decimal. Okay, this big long decimal is not exactly it. This is an approximation because radicals often fall in the same world as pi. It's an irrational decimal. It goes on for forever. Okay, but we have enough information here that if I type in 2 square root 2, I get that same big old long decimal out to know that these two things are the same. Now the catch is that you're probably not going to know every single perfect square that's a factor of every single number. Okay, so being able to find those perfect squares is a little bit tricky. So I'm going to give you a way today that you can simplify a radical, can simplify a square root without having to automatically just know every single perfect square that's a factor. Okay, we're going to sort of streamline the process and guarantee that we can get it simplified every time. So let's say we want to simplify the square root of 60. The first thing that we are going to do is we are going to prime factor the number. Okay, so good news, we've already talked about prime factoring, right? It's the tree thingy. You should know that it's prime factoring. Okay, so 60 splits into 6 and 10. 2 and 3, 2 and 5. And when we talked about prime factoring, I said it'd be a really good idea to put it in numerical order. This is the time that it's a good idea to put it in numerical order. Okay, so now instead of having the square root of 60, I have the square root of 2 times 2 times 3 times 5, which is, right, all of this stuff is the same thing as 60. They're equivalent. Okay, the next thing that we are going to do is we are going to circle any pairs. Now, I'm putting these quotations around pairs because if it was a cube root, we would want to circle triples. If it was a fourth root, we would want to circle quadruples, right? 4 of them that are the same. So this process will work for simplifying any type of radical. And I do not know all my numbers to the 4th power memorized, so this is exactly what I have to do. Okay, so we're circling any pairs. So inside this, we see 2 and 2. Okay. Our next step is then going to be that we're going to pull the pair in front of the radical. Okay, now here's what's really happening. By circling a pair, I'm forcing a perfect square. 2 times 2 is 4, and the square root of 4 is 2, right? That's something I can take the square root of. A perfect square is always a number times itself. Now, this is one pair. So one pair, it comes out one time. So I'm only pulling that 2 out one time because 2 times 2 is 4, but the square root of 4 is 2. Okay, anything that's not a pair still gets left over inside, stays where it's at. Okay, and then our last step is that we are going to multiply anything that's in the same position. So this 3 and 5 are both left inside, and so they get multiplied together. So to simplify the square root of 60, we have 2 square root 15. And just like with the variable, this actually means 2 times the square root of 15. Okay. So let's look at another one here. Let's say we want to take the square root of 300. Slightly larger. Start the same. Okay, so maybe you say 30 times 10. 3 times 10. Now, I'm specifically choosing to prime factor it this way because now we see 10 and 10. If you recognize a pair at any point, you technically can pull them out, right? Because we would know that 10 times 10 is 100 and the square root of 100 is 10. The problem is that you have to be really careful and make sure you're not using any numbers that have a branch coming off of it. Now, I'm just going to pretend, because we all could have split this up a different way, that we don't see any pairs, and we get here. Okay, so our prime factorization is 2 times 2 times 5 times 5 times 3. Okay, and so now we have the square root of 2 times 2 times 5 times 5 times 3. And so our next step says that we are going to circle any pairs. So I see a pair here, and I see a pair here. Right? Those pairs are getting moved in front of the square root because I can take the square root of them. Right? The square root of 4, 2 times 2, the square root of 4 is 2. The square root of 5 times 5, which is 25, the square root of 25 is 5. And then what I have left over is a 3. Okay, anything that's in the same position gets multiplied. So 2 times 5 is 10. Square root 3. Okay, now I do just want to write this slightly differently here. So if we have 2 times 2, that's 2 squared, and then we're taking the square root of it, you might say, oh, well, are those two things just canceling out, right? Is this exponent of 2 and the square root just canceling out? Yes, that's exactly what's happening. They are inverse operations. Addition will undo subtraction. Multiplication will undo division. Square roots and exponents are what undo each other, right? They just cancel each other out. So that's exactly what we're doing by finding those pairs. Now, there's a couple things that then we need to be careful of. So I already sort of mentioned this one, but just to make sure. So if I say, okay, what is the square root of negative 16? What is the first thing that your brain should say, right? Hopefully in your brain you're going, oh my gosh, that's a negative. So our answer here is a no real solution. There is an answer that involves I in the imaginary number set. Okay, but for right now in the set of numbers that we are working in, we don't have an answer there. Now I'm not going to pick a number here that's very large just because I want to show you that it happens, but I also don't want to make our lives miserable. Let's just say for some reason you're working with 64. Okay, and when you look at that 64, you just are kind of in the groove of working and you forget that that's a perfect square. Okay, and so you start prime factoring, and maybe you pick 2 and 32, 2 and 16, 2 and 4, 2 and 2. So 1, 2, 3, 4. Uh-oh, I missed one. Oh, 2 and 8, 2 and 8, 2 and 4. Dear Lord, I couldn't even find my own mistake. So 1, 2, 3, 4, 5, 6 twos. 1, 2, 3, 4, 5, 6. So now we have the square root of this. Okay, so you're moving right along. You're circling your pairs. And all of those come outside. So now you get 2 times 2 times 2. Nothing left inside. 2 times 2 is 4. 4 times 2 is 8. And so we just get an answer of 8.